do, or you can just give a completely different presentation.
I think I will just do live, and based on what you showed so far,
for it. Yeah.
I'm just going to do some cool stuff that are not like lots of documentation. But
and after this, Sebastian will also show a pre-recorded video if you want to go watch it later. That is available on Vimeo, or I can show it. I can share it while he's setting up. I gotta go find it, but I'll share it.
So hopefully you see my good screen. I don't know which one you see.
Yes, we do.
Okay, but I've got two screens. So I'm just putting in the chat some links and useful information as a first step, which is mostly the video that I've initially recorded for today. And then I guess the next link I'm putting in the chat is there's since you were presenting, Masha, some example with Python and Jupyter and things like that. I think there's a toolkit that Kitware is doing that is named ITK, that has like lots of algorithms, mostly done for medical imaging. But in terms of segmentation and so on, you could reuse some of those algorithms for what you are doing with your type of data. So that could be a good resource to look at down the road as well.
Segmentation is one of those things that we could have another 2 webinars on. So I kind of intentionally skipped over it.
Yes.
That's the next one. That's the next.
So the next section I put in the chat was 3D visualization tool. Today we saw Mayavi that is Python based, but it's based on VTK, which is the visualization toolkit, which is also a library that Kitware is supporting and making open source and available for the community. And two applications that we build on top of that library are TomVis and ParaView. So ParaView is more designed for parallel visualization for big data and meshes and simulation, but it can actually work with the data that we've seen today. TomVis is more designed or geared towards tomographic data. And since you were saying that some of your data get scanned or are coming from tomography, they might be like, TomVis may have some tools or capability that may more be in line with the type of data that you're dealing with. So that's also another software that could be interesting to look at. Both ParaView and TomVis are free and have support, so you can, like, there's forum online where you can ask questions and so on. And I guess what I want to do some live visualization and demonstration today will be more web oriented. And for Jupyter Lab, actually there's a ITK widgets, which is like a kind of interactive cell that can live in your Jupyter environment that rely on VTK.js, which is a JavaScript implementation for visualization. And like most of the visualization we've seen today with Mayavi could actually be done within that widget. And the idea is using your WebGL or web browser component to do that. So also a good link to go about. And this ParaView Glance, which is what I'm going to show you right now. So ParaView Glance, I've loaded a bunch of data, but I will just start from scratch so you can see how to do or get somewhere. So if I go to the ParaView Glance link that I just put right there, you will go to a website where you do have some documentation, example, and gallery and what's not. But you can also like just run the application itself. Like there's no install step or anything like that. There's some sample data set that you can play with, but since Masha shared some data earlier today, let's load, I guess, the first one, which was the raw file that I think Mike shared. So as you can see, since it's a raw file, they mentioned that you need to specify what is the data type, what is the dimension. So we are 244, 234, 234, and it's 19. And as you can see, there's like effective size and just like a confirmation that whatever based on the data that you loaded, the dimension you're provided seems to be correct. I mean, you could have swapped the width, the height, and the depth, but other than that, size-wise, it matched our expectation. And you can see the data that we were looking earlier right in 3D there. You can also like see the distribution on the back here, like that's the histogram of the distribution of the data. And here we can see the void or the VUG, I think that's how you call it.
Yes. So just a comment, these are the Z direction slices are larger spacing than in X and Y. So that's why it looks squished.
Okay.
That's just the way it's an experimental setup within a CT, medical CT. That's why the one is. So you could multiply the 19 dimension 3 times to get it in a more proportional form.
44, 19, and you said on the Z it's like 3 times bigger.
3 times, so, yes. I think that's from memory.
But
yeah, there we go.
That's what it is.
More like it, yes.
But that's good because then you can see like how things
I'm gonna go double check myself, but that information is on the portal somewhere. But that's a typical,
Yeah. So here is like the visualization of actually those VOG in 3D. You can change maybe reduce the spacing to increase the quality maybe of the rendering. There's a way where you can just take a screenshot. So like if you've got a presentation, you can make it transparent, save it, download it. And then if I open it here, it's right there, and it's the image I just made right there. So that was kind of fairly quick to just drag and drop like some file and use like a tool that you don't have on your computer, but just use browser. You obviously have some option to split the view and start looking at the data also in form of slices. So you can like turn those slices in the 3D so you can see where they are located. The same for the other axis if you wanted to. That's the wrong one. And you can see showing up in the 3D depending on if you enable them or not. So that was kind of the first data set.
So where this would be useful is, for instance, if there is a pretty large image and I might not have the memory for it. So what are the limitations of this on the cloud behind this glance?
So Glance is really just using your local computer. So it really depends on your local computer. Like truly it's just a JavaScript file. And technically, depending on the data that you're loading, it's just like an HTML. So you can like just share the HTML. You double click on your file and then you drag and drop your data on it. So the limitation will be your hardware and what the web allow you to do. Of course, you can load ParaView to load the data in the same way. And if you look at the video that I shared show you how to load your data in ParaView, do some visualization, and then even export the scene in 3D so you can use Glance to get to the same stage as what you were before. And actually, if I have an export here, and I can just drag and drop a scene that I've exported with ParaView that was computed with ParaView, where the geometry and so on was processed through some contour filters and visualization. And
so we have a question. Does it provide scale bars in 3D?
Not within ParaView Glance, like the
download ParaView on your computer. Yeah. Okay.
Yeah. And here, for example, you can start toggling elements of the view or that I've generated inside ParaView, for instance. And so you can start looking at data. All of that was generated with ParaView using the tool, but the other part that I wanted to show you with ParaView Glance is, Okay, let me go back to glance the website. There's a latest version which has like more maybe capability or might be less stable. There's a feature that I want to show on that one. And what I want to load is the other example that you've loaded, Masha, which was the oil.
Kitten limestone.
Thank you. As you can see,
From,
it's not
from
my
Imperial
expertise.
College.
And 225. Is there any scaling that I should do?
No, that one should be 1-to-1 inches. 1 to 1.
Good. So I'm just loading that data set, and like you could tell, you were saying that there was 3 values, 1, 2, and 3 or something. Yeah. So by changing the location of my transfer function, I can see the, I don't know what you call it, but the blob.
Oil blob, yes, surface of the oil blob.
So you can see the blob right there. I can add like another Gaussian also to highlight the intersections with the rock around that blob. And like I did before, you can also look at the various slices. So if I take the Z slices, you can see those 3 values, white, gray, and black. But if I wanted to use the same color map, I can also use the same color map as defined in the 3D view and just use that as well right there. I can have different settings and pick some other color map if I wanted to. I can also use the opacity. So right now I'm more highlighting the blob and the rock section with the transparency. And like I said, this is just a visualization tool that lets you easily browse through your data, maybe experiment or navigate through the visualization, and let you create like some nice screenshots on some of those visualizations that you can save or download.
So how can you export? So do you need to start a trace, or how do you export this as a script that you can redo later or re-execute later?
So because ParaView Glance is just plain JavaScript and nothing more, the only thing that you could do is you could save the data, and what save data will, or save state, sorry, I should say, will do is it will capture all your graphical settings of like or transfer functions that you may have defined, the color presets, maybe the position of the slice. If you started with like 2 views or 4 views, and what is actually the layout of your data, for instance. And that file could be shared and reused, so people will arrive to the exact same state as you were before in terms of visualization.
So for that, then if you wanted a sort of a script of some sort, then you would still have to install ParaView on your computer.
Yes. So for example, if I load, actually I wanted to load another data set. So I'm just reloading the web page to just reset the application right there. But the other data set that I wanted to show, I think was in my download. And it was this one. So that one, since it's a VTI file, it has all the information regarding the dimensionality. So I don't actually need to do any of those information about the dimension. Yeah. That was already
And for
captured.
everybody's information, this is once upon a time, Patrick Toleri from ParaView was in my short course on digital rocks. So this is a fractured carbonate that also has some vugs from Dr. Pope from our department. that I got initially as one of the lighter latest data sets to work with. In the meantime, we lost the information on the course. It was never uploaded to the Digital Works portal for that reason. However, if you want the data, I can share. So just let me know.
So here you can truly see the
combination of
vast, right?
bugs and fractures, yes.
Yeah.
And actually there's some messy fluids in there too. Just FYI, it was a random core picked up in the lab and scanned. So, there we go. Yeah.
So you can see the slice there. I mean, I can pick the Z orientation, and if I show this on the 3D, you can move it along, and same as before. But the goal really of ParaView Glance is more like a lightweight tool that you can use to just like start navigating through your data and do some visualization from that. If I do similar things with ParaView, so what I will do is just take that same data set that I was just loading right now. And how much time do I have? I didn't check my So here by default, ParaView will just show the volume as an outline, but if you decide to show the surface and the field that you're looking at, you can see that it's actually a cylinder. You can clip it through just a plane, so you can see inside the data, the remaining sections of the data. And I'm on my laptop right there. I could use for the clip a cylinder, so I could extract. So I think the information was, I could extract possibly the, remove the surrounding like Mike was showing earlier, and just like focus on the data inside. And just to show what Masha was explaining about the contour filter, I'm just going to run the contour filter on that subset to just extract the vogue surface. And I guess, I don't remember, I think it was around 80, that was a good number, maybe lower than that. But so what we are computing is actually the surface of those vogues right there. And since you were asking for Python, if you go in View and you show the Python shell, you can have access to the different filters. So source. So here I've got my contour filter, and if I do list properties, I will have all the property that I can tune from here. And typically, if I look at isosurfaces, you can see that right now I put like 80, but I could say I want actually 20 and 30. As you can see, they are right there. And since I didn't trigger any render, by just clicking on the 3D view, I did trigger a render. So if I go back to my 80 earlier and do render, it would actually do the rendering of what I was looking earlier before. Also, the other cool things for Python is if you know to use the UI, the thing that you can do is if you go in Tools, Start Trace, and you say, oh, actually, I want like 120 right there. I apply my changes. Once you finish the computation in the tools, if I stop trace, what it's going to do is capture every actions that happen on the Python side, so you can like fully script and understand what was happening there. And without like the overhead, here is kind of the part where between the start and stop, I change the ISO surface to be 120. And that's, or you could also learn or to do some Python code right there while using the UI of ParaView. And I think I will stop here and just like open the floor for questions. You're muted, Misha. Sorry.
Excellent. Thank you very much. And I want to chime in is that for the visualization challenge, we do actually want to collect scripts. So you've seen Dragonfly and ParaView. Both of them have this scripting feature where you can record the trace of what you're doing. You can also post cleaning up later. Not everything that you've done on the screen needs to be shared, but there's a dance between whatever you're trying things out with and what you actually export later. But we actually want working scripts to share because that way we can start everybody with good visualization scripts that use the data on the portal. So the scripting features from notebooks, from different Python environments, from advanced visualization tools are very important. Any questions for Sebastian or for anybody on this? So we have about a little less than 10 minutes left. So to wrap up, please ask any questions. Again, you can use chat. If for some reason sound is not working very well, you can unmute yourself and ask a question. Don't be shy. Is there a Python manual for ParaView? That's
Yes, I mean there's lots of tutorial online. I guess the best. So what I show or what I did in the background was just exporting the scene here and importing it in ParaView Glance so I can easily share the visualization. But moving on the documentation, if you go on ParaView.org, you will have links on resources in terms of guides, tutorials. There's also a blog post that Kitware folks publish some tips and tricks on how to do things. And there's indeed like some tutorial showing you how to convert some of the volume data or data structure into NumPy array so you can do processing with NumPy and go back and forth between whatever ParaView or VTK is expecting versus what NumPy is dealing with. So yes, I would encourage you to go through the online documentation. There's obviously a lot, but also within ParaView itself, if you go in help, there's like some PDF with a ParaView guide that is available freely. And I think what just happened is downloading the 47 megs PDF file, which is like a full book explaining how you can use ParaView. And all of that is free and open source. So, and you can make plugins that could be just Python based or C++ based, whatever suit your needs, basically.
any other questions? Again, so I will figure out a forum and I will probably add everybody who registered to that forum and you can remove yourself. But this is where we can continue discussions. Obviously, we could only really scratch the surface. There is a lot that you can do. A lot of it depends on the data you're looking at. So nobody can give you a recipe that always works because that will change as the data sets change, and that's the fun. However, effective visualizations can really provide insights, especially in three-dimensional world. When the phenomena you're looking at are three-dimensional, there's not much gaining insight through two-dimensional slices is difficult. Okay? So just a reminder again, visualization challenge is open till December 1st. We have what we call static image, so beautiful image, but all single image, visualization video, and also 3D prints. So you would use this surface visualization or STL files based on them to print in 3D. We do not expect physical sample, but we do expect an STL file that is printable. So in that sense, that's definitely a challenge because they need to be cleaned up and post-processed a lot to actually get something to decently print. So
I guess, Masha, since you were saying like it's important to have scripts that works also, when you're interacting with the UI, there's an options in preview where you can save the state. And there's different format. There's like an XML format that captures those properties, but there's another one that is just a Python state file. And that actually capture every, like from nothing to loading the data to the processing and so on will be captured as a Python script. So that's something that could be interesting for you if you use ParaView to at least capture that, so you know what are the settings and so on, and could possibly reload or execute that script to just generate the same visualization, assuming the path of the file that was stored is the same, but you can easily edit the scripts to fix the path of such a file. Sorry for interrupting.
Yeah, no, that's great. And a lot of, because we'd like scripts that work from scratch, if possible, with the understanding that you don't need to supply data, but you can point us to where data is. So in that sense, that would be a great addition. One warning, and that all of these scripts, they actually can capture everything, and quite literally everything. So that sometimes needs a little cleanup, but you can basically walk through the file and try to identify where the key things are that you want to show, and just then edit that script to show only what you'd like. But they will definitely re-execute everything that you've done on the screen. So that's basically where all of the software is going. Frankly, if you're building a visualization software and you don't have that capability, then you might need to rethink your strategy. As our advanced visualization shown here is showing. All right, any other questions? Well, thank you, everybody. And thank you for surviving through near end. I will email everybody with the videos. So we have already posted some of the code on GitHub, but we will post the videos of this recording for your reviewing pleasure. Okay. And we don't have, I would also like to thank, so we've exemplified the Dragonfly and ParaView, but we also had 2 more sponsors, Southern Database Big Data Hub, as well as the Salt Systems. And I think we have somebody from the Salt Systems here. Zhuang, if you have any questions about their software, he is on this chat, so you can maybe ping him, Zhuang-san.
Yeah, here's Zhuang, and I'm from the Salt System. Feel free to contact me if you have any questions.
All right. If not, I thank everybody.
40 people
Again.
through. But we did well to get 40 people through.
Hey, again, it started with 56, 40 survivors at the end. I call that, I teach a lot. That's a success. There you go. So Zhuang, there is a question about the software if you want to. What the Salt Systems does. They're more flow simulation oriented. There's Abacus. Yes, Abacus is a finite element software. In terms of digital rock stuff, though, finite elements and digital rocks, they're difficult to put together.
We do have a bunch of softwares, and most of them are under a brand named Simulia, if you are familiar with the Salt system. And for fluid flow simulations, we have 3 codes. One is Abacus CFD, and the other 2 are based on LBM, lattice Boltzmann method. They are PowerFlow and XFlow. We also have a digital rock approach based on PowerFlow. So actually,
so if one wanted to, a lot of participants here are students. So is it possible to get a free version of the software for student use, or how does that work? Or for some limited amount of time?
Yeah, thank you so much for your question. So I know for Abacus, they offer like academic license for the students, but not sure about like PowerFlow, XFlow also.
Okay.
Yeah.
So again, there's a question about the video. I will I will blast everybody with a couple more emails after this with all of the trainings materials from this session, and I will also link them to Digital Rocks portal. So you can also go to that visualization challenge page that is on Digital Rocks portal.
The ring artifacts, Masha.
Ring artifacts, 2D images, so ring artifacts is something that shows up in CT imagery. So yes, in CT you might have them. The SVM image does not have them. Oh, removing them though. That's a lecture on its own. Removal of noise from CT data is difficult because it's extremely nonlinear noise, ring artifacts included. So the best modern reconstruction techniques do that on the hardware end. On the software end, once the image is reconstructed and you haven't removed them, that's extremely difficult, and it's kind of like a trial and error to remove. So the best is, yes, there's a paper by Stefan, now I'm blanking on the last name, Dorothy Wildenschild and Adrian Shepard.
I think it's
Schluter, yes. So there's definitely if you need us, I'll email you back with this papers, but you can also, so it's the last name is, let's put in some last names. I'm gonna do this, Wildenschild.
I'll pull up the link here in about 2 minutes.
Dorothy, yeah, Dorothy Wildenschild has a unique combination of names. If you know how to spell it. Same as mine. If you know how to spell me, I'm the only one. If you don't know, oh well. That's the beauty. So if you look through her Google Scholar, you will be able to find, this is Stefan Schluter, German last name, and Dorothy Wildenschild and Adrian Shepard. They have a paper on removal of the noise from X-ray images. There we go. Mike has been quick.
It's definitely correct, though, that if you can get it in the reconstruction stage, yeah, that's the right place to do it. And if you're not, then you're going to be dealing with all sorts of issues because you're really removing structure from your image, and there's always challenges of telling, well, what's a structure and what's an artifact, particularly when it gets to the length scale of some.
And when I say the noise is non-linear, it's not additive, it's not simple, it depends on multiple things, both the X-ray energy and the material it's passing through, and whether it's some of it is bounced off the material, some of it goes through. There is sometimes, well, especially with the harder X-rays, there is some much more complex interaction with the material that we don't necessarily model when we reconstruct, okay? So that's where actually, and porous materials have a lot of surfaces and different minerals, and there's a lot of different interactions that are kind of like averaged in that little voxel. And that's why that's where noise in the images is coming from a lot of times. So in that sense, it's the best done on the sort of like right there when you're imaging, playing with the combinations of inputs that go into reconstruction. Once the image is done, it's much harder to remove.
Yeah, for sure. It's the first choice is always to correct it in the sinograms or in the X-ray projections before you've reconstructed, like what Masha just said. I'll just point out that of the 2 links that were shared in the chat, the second link to TomoPi most likely gives you methods for solving it there prior to reconstruction. However, if your data has been handed off to you, if it's already been reconstructed and you don't have the raw data, you don't have an option to reconstruct it for yourself, then you are stuck doing the best you can in the image domain. And that is the topic addressed in Dorta and Adrian's paper.
So I personally don't do X-ray imaging. I typically am on the algorithm side, but I work with a lot of people who do, so I know quite a bit about it. And from what I know, it's best removed at the time of reconstruction. So TomoPy is the software. I typed it in. Tricky question. How do you know what we see is what it is? Well, we don't, because the best view that you have is the one you're looking at. So as in everything in porous media, you have to look at multiple sources of data. All of those multiple sources will look at different things. So say one thing is that you could have a measured porosity. Well, measured porosity will look into helium porosimeter, and it will give you an average value for the entire volume. That volume is more likely than not much bigger than the one you imaged. So you really compare two slightly different things, and they're on different scale, and they're done in different way. And that's the best we can do. So we have to look at multiple sources of data. A lot of times so there was an example of the super resolution, and that example is on the DigitalWorks portal. What they did is like, CT is great because it's in 3D. CT, whatever has similar density will look similar in CT. And well, a lot of carbonates and sandstones, they're all about 2.6 gram per centimeter cube density. So they're going to give a similar signal. So I cannot do mineralogy, but I can supplement it with different type of microscopy images that come only in 2 dimensions. So now there's actually a lot of advancement combining those 2D information that has a lot of textual information, not without its problems, because SCM will also average a slight volume and see sort of like, you will see depth in what's a slice and it's supposed to be a single plane, but you can combine those with 3D data, at least locally. And then what helps in propagating that information into 3D image is the most advanced deep learning. That's my 1-sentence explanation. There's probably 5 papers that I need to cite here to go into really details of the most advanced techniques that combined give us the best description we have on the pore scale.
No, Masha, I think that the questions are indicating that there's some market for advanced image processing.
Oh yeah, no doubt.
That's what I was asking Masha for help last week. I would like very much to organize a detailed scientific image processing course, but it takes a lot of work to put together that course, especially if you wish to address all of the specific artifacts in the relevant imaging modalities, which could be FibSim curtains or alignment or ring artifacts or blur or noise, etc.
We had the way a lot of my education efforts have started. Were 2 short courses in 2011 and 2013, where Dorothy, Adrian, and I got together to teach a course. And I have now expanded version of those lectures that are mostly focused on X-ray tomography. That's just by the nature of what we all started in. And I teach a graduate course at UT. There's a YouTube version, well, not the very good version, but there's a YouTube trace of those lectures on my YouTube. I've been posting things pre-pandemic, and now in pandemic, now I'm posting, but it's actually behind the UT lectures or UT firewall, if you will. But I used to just post things on YouTube. So you can try to search through those. It's a constantly evolving field of different types of imaging. So there's microscopy that needs a whole separate way of dealing with things. And then there's X-ray imagery, which is the most common 3D volumetric. So yes, things are definitely easier and easier to find, but there's a lot more work to be done. So I'm hoping to actually start sort of like a line of lectures. This is the first one of those that are kind of using and pointing to data in the DigitalWorks portal, so that context is also provided with the data. We're about to have the first reconstruction data set on the DigitalWorks portal once I actually stop dealing with preparing stuff for this course and actually go curate that. DigitalWorks portal is waiting for me to actually clean it up and publish. But there's actually it's a large data set. It's 250 gigabytes of data pre and post reconstruction from Ghent University. So yeah, it would be definitely good to put something out there that is a little more coherent than my ramblings on YouTube.
That's terrific. What is the timeline for that?
The timeline for
that the pre-reconstructed data set?
It's gonna show up. It's tied to a paper that is about to be published, so within next week. I should have done it last week, but oh well.
Yeah, I'd like to maybe I could use that as a benchmark for people.
There's a handful of curators. Javier is one, Ankita is somewhere around, possibly still, and one more. So we are doing things kind of by hand. That's another thing where we need to expand the community. Data sets need to, basically the review of data sets should go similarly to review of data, of journal papers. Just for quality, because whatever you post, there has to be a quality check, and that's right now done manually, and that's a limitation. So if you're ever waiting for the publication of the Digital Works portal datasets, that's because it's going through the single bottleneck of 3 or 4 of us reviewing. Any other questions, comments? Again, feel free to unmute yourself and chat. This is now open chat session. Did we answer all the questions? So, the FibSim question was, yeah, curtains in FibSim or SCM, high resolution SCM, are common. A lot of people try to either do them manually or walk around them manually. Good news is that they're fairly visible and a clear artifact. You will rarely have features that kind of slice across the entire image in a straight line. Too straight of a line in a natural porous medium is not real. So you can try to identify it that way. But there's not, I think there's no, plug and get a result solution out there yet. You always have to kind of do visual check for FibSims.
All of these artifacts are areas where, neural networks are a good option if you have a hard time, if you can visually see something in an image and it's an artifact, but it's difficult to remove with, sort of conventional image processing tools. I think those are good candidates where you might take a neural network and try and train it to do it.
I've actually been trying to do this using covenants by creating a random ring artifacts on the images, but it didn't come handy. Most probably because of the data size that I gave to this, the number of images. Like and maybe also the generation was not in the way that an old X-ray device was created.
I would recommend if you want to do, ring artifacts, a lot of times they come up because you have some sort of dust or something on the scintillator in the imaging device, and you end up with this stripe that's sort of revolving around in the reconstruction step. So if you want to,
one pixel that moves around, that is corrupt. Yeah.
So what you want to do is reproduce that before the reconstruction step. So take some data, that's sort of clean, and stick an artifact in it, and then reconstruct it so that you generate an image, a ring artifact in the data. So like you could, if you took data that hadn't been reconstructed, you could easily introduce ring artifacts, and then I would train it based on that. Because if you're using, if you're trying to create just a ring artifact later in this process, I think it'll be, it's almost like removing it, right? It's a little bit opaque what the structure should be. So I would that's how I would do it.
I would say we, I gave a talk in May on the idea of not correcting your artifacts. Specifically, The question came up 5 minutes ago is how do you know what you're looking at is real? And you don't. But your intuition and your visual processing that's happening in your visual cortex is much better than a naive computer algorithm. And if you look at a ring artifact, you can immediately tell, oh, that's a ring artifact. And when you look at the pixels that maybe straddle a ring artifact, you can say, well, I know that these are real poor. These dark pixels are real poor. And I know that these are artifact and they're fake. And what you can do is you can train a neural network. You don't have to train a neural network or a model to correct the artifacts. You can just tell it to recognize things and basically see through the artifacts the same way you do. So if you segment pores on a clean image, the neural network will learn to label which pixels are pores and which pixels are not. If you segment pores on a corrupted image and include that as training data, it will learn, oh, when I see these corruptions, I'm learning to recognize what you consider real and what you consider fake. So if you have a training data set that includes the artifacts, then the neural network can compensate for it. And it's basically doing the same thing you're doing. Rather than trying to produce a clean image, which might be nice for a figure or a manuscript, what you want is the high quality segmentation. And so you can train the neural network to skip the correction. Instead, just give the correct segmentation the same way you would do by eye. I'll post a link to, it's a rather long webinar. It's like an hour and a half on this one topic, or an hour and 20 minutes, but I'll post a link if you wish to see it.
There's a question on the microporosity. You can segment where microporosity is. You have to have some additional information on what is the scale of that microporosity, because by definition, you're not resolving it in the image that you're looking at. But at least you can see how is it connected in 3D, and then you can equip that space with something that you know about it. In terms of being able to handle now a large model that is based on that, poor network models are your best bet. I've been doing with some of those. I've been dealing with some of those models. I have an internal code that is, well, it's not clean enough for posting, but I think OpenPNN is starting to have some network creation ability on multiple scales. So I can definitely, if you look for Mehmani and Perdanovic PNN papers.
To do that, you need information about the structure of the microporosity from SEM or something.
And if you don't have it, then you have additional layer of uncertainty. So you need to, so there's a 2014 paper where we actually didn't have that. So we kind of equipped the network with multiple types of information. And you can see then like where you're going with that. And you can do sort of what I would call sensitivity analysis. So in that sense, you need some sort of uncertainty quantification of on your inputs, because that's the problem. You're creating microporosity, but if you don't have all of the detailed information within, you're guessing somewhat, right? Another way in direct simulation would be lattice-Boltzmann. There is something called grayscale lattice-Boltzmann methods. Again, the problem is you equip the microporous space with certain features. Then the question is, how do you check? There's again a number of parameters that could be set in different ways. And your image, your original image, the starting one, doesn't tell you that. So you need to have additional source of information. And you need to have a parallel computer to simulate, because lattice-Boltzmann right now, even on a single scale, is too much to handle for two-phase flow for a lot of times. So then if you also have microporosity, it's essentially reservoir simulation on small scale. Okay. Okay. Any other questions? From people. So super survivors went on and are here for additional 20 minutes. Yes, did I interrupt somebody? Bit of a lag.
I think that was me. I think I was.
Oh, okay.
Exit on the. We're down to 12.
All right. So. Well, if there are no more questions, we're gonna close or certainly stop recording. Thank you, everybody, for insight. Yes, so there's much information shared on chat. So when I get the recording, I'm also gonna get a chat output. So I will share both for sure. Actually, if I get to it, I'm gonna compile one pager with all of the information shared in chat, because that's a lot of information right there. That's also the reason why I wanted to go with Zoom, because that's what we have because of the class recordings. We have all of those capabilities streamlined. So
if we do a Google form, we can just put this stuff there, right?
Correct. Yeah. So that's why I also want to do, like, just to have one page so that we don't have to repeat the information that we have shared right now. And that can be a good starting point for people who want to catch up. Well, and ourselves too. I'm like, what was that paper? That kind of a thing. All right. I'm going to stop the recording.